Good morning, everybody. Welcome to day 2 of the workshop. We're starting with a panel on, let's say, the human risks of space exploration. We will have a panel discussion later, but we will start with a keynote presentation from Maybrit Kuipers, who is one of the flight surgeons at our European Astronaut Center. So working very closely with the astronauts. So Maybrit, the floor is yours.
Okay, good morning, everybody. So, first of all, I would like to say thank you to Poland and the Ministry of Science for being a very gracious host, and the organizing committee for putting this all together and bringing our teams together. I must say, I am very excited that this is now happening because I've been wanting this type of conference to happen for a long time. I work at the European Astronaut Center in Cologne with a quite small team in the medical operations team. So with flight surgeons, we have physiotherapists, exercise specialists, radiation specialists, psychologists, and so we work closely together, and we, as Angelique mentioned, work very close with the astronaut crew and support their missions. So we got a pretty good idea of how their health and well-being is affected by spaceflight. And we also work on preparing for the upcoming missions, so the lunar and Mars missions. And we do that closely with our international partners. What I want to talk about today is about not only the human risks of space exploration, but also basically our priorities. Because frankly, we're kind of running out of time to get some critical answers. And what I think is so great about this conference is that we're bringing operations world close to the scientific world. And what's also nice is that we're working across disciplines. So basically life sciences, physical sciences. We also have engineers here today. And I think we really need this to accelerate. And this is also, I think, where Europe is unique or better than perhaps other places in the world, where we can actually, because we are a bit smaller, we are also more agile to address some of these critical questions. But of course, we cannot do it alone, and we have to work with the international community to get where we want to get. So this was already discussed yesterday, the Explore 2040 strategy, and this is where it's finally being made possible to have this exploration-focused research. And basically this means that we can have some operational priorities and communicate this to you, and hopefully by the end of this presentation you will have a bit clearer picture of what we mean with that. And we want to understand the actual risks and develop solutions that will enhance the safety, but also sustain human health and well-being, right? So that's our primary goal. We want our astronauts to perform well and stay healthy and come back healthy as well. But we have some challenges. So first we have this near rock, and then in some future years we'll have this far rock as a destination. And at its closest point, Mars is 145 times further away than Moon. So you can see that the challenges are going to be exponential when we go there. The good news is we already have a vast body of knowledge from the ISS mainly, but also from other previous space missions. And we know quite well what are the medical risks and hazards of space environment. So basically shown on the slides here, we have isolation, confinement, microgravity, the enclosed environment, acceleration, noise, we heard about that, ionizing radiation. And we know that basically all human systems are affected to a more or less degree, and the appearance or the phenotype of those problems don't all appear at the same time. So there's an evolution, and some things we adapt well to and some less well. So when we venture out further, there's going to be a little bit of a change of scenery. So yesterday we talked already a lot about radiation and how that is different when we go to the moon and to Mars. Altered gravity will be a thing. So when we are in Leo, we go to zero gravity, which is a main contributor to a lot of the physiological changes that we see in our astronauts. But then we go back to the moon, we're gonna have, gravity transitions, and how does that affect our astronauts? And same with Mars. Remoteness, that speaks for itself, right? And together with remoteness comes more isolation, extreme and confined environments. So when we look at basically the physiology, these are some of the big ticket items that a lot of you have been working on and are very well aware of. And I'm going to zoom in on a couple of those today where we think not only our priorities lie, but also where our opportunities lie. So basically, where's Europe good at versus NASA? Because I think somebody mentioned it yesterday, like if we're all going to address the same issues and work on the same problem, that's not very efficient. So we need to also try to focus on things that we are excelling at and looking at the resources that we have in Europe and make use of those. So on the one side, we have the physiological effects, and on the other side, we have the countermeasures. Again, with ISS, we learn a lot about countermeasures. We have great countermeasures on the ISS that are really helping our astronauts to remain a good level of fitness. But we're not going to have that luxury in the smaller exploration vehicles. We're not going to have 3 different exercise devices. So we really have to start thinking smart, how we can be more efficient. And the same goes for all the other areas of countermeasures. We really need to start thinking about those and newer countermeasures that are more effective, but also low mass, low volume, right? We cannot bring as much as we have, and we'll not be able to resupply as much as we had in the past. So 3D bioprinting, I think, will definitely be a thing that we need to look more into. But also, how are we going to model things? Like, how are we going to do the research on exploration? And that's where I think there's going to be a whole session on that with Dr. Hahn on 3D tissue modeling, which I think is going to be a very nice area where Europe can really excel. We're already very good at this, and I think we need to excel in this area to get a better understanding of that new space environment, like the Gateway, like the lunar surface. So when we talk risk, we have to consider a few things. I don't think this matrix is new to you, but it's good to keep it in the back of your mind in this presentation. So on the one side, we have to consider probability, and on the other side, we have to think about severity or impact of a certain issue. And this presentation is mostly focused on human health, right? And to be honest, NASA did a very good job in putting a risk map together, where they've basically mapped out all these things. But when you see the map, there are a lot of yellow, red spots for the Mars missions, and there are quite a few also for the lunar missions. So there's still some knowledge gaps there. What you also have to keep in mind is the different scenarios, right? So we have short duration missions up to 3 days. So the first Artemis flights will all be short duration. And we heard yesterday, like, is radiation going to be a big problem on those short duration flights? Probably not. But when we go further, yes, if we go to the lunar surface, and I'll get into that, there might be other issues at hand. So it's not just about how long and how far you go, but also the crew tasks, the tasks that the crew have to perform in that mission. And this is really where operations come in. And this is why I also think for the next conference, my suggestion would be to also have more crew attending to get their feedback on their perspective, right? So the first upcoming missions, as you see here, we have the comparison of the ISS to the Gateway station, which is going to orbit in this elliptical orbit around the moon. And yeah, you can see the difference in distance. But what is also interesting is the difference in size. I hinted at this earlier. So the ISS, as you can see, much larger, more modules, more capabilities than the gateway when it's fully assembled. So in volume, you have to think about it's 1/6 of the ISS. And it's not just the outer, like total size and volume, but look at the inside. So on the left, you see Luca Parmitano in the ISS. He's a pretty tall guy. And I mean, you know, ceiling and floor and is all basically the same on the ISS, but you can see he can stretch out pretty much. On the other side, you see also Luca wearing the helmet there on the left in the IHAB mock-up. And this is why we do, you know, human-in-the-loop testing, is to actually see, like, you know, how is this going to affect us operationally? So the internal volume is going to be much smaller. So that's going to have very much an effect on how the crew will work, but also, for example, perform exercise, and there are limitations with that. When we look at the interior of the Orion, so this is one of the few pictures that I could find that are publicly out there, to show you what it looks like when the crew are in their seats on the inside. And there's not a lot of volume there. And we know that actually next year, this crew is going to fly to the moon, and they're going to do the test flight. So they're not going to land on the moon, but they're going to do a flyby. Basically replicate the Artemis 1 mission, but they're going to do a lot of testing and certifying of everything, because it's a test flight, and it will take about 10 days. So they will be in this small capsule for 10 days. Do we have countermeasures on the Orion? Yes, we will have this device. It's called the flywheel device. It's much smaller and it has much less capabilities than obviously what we currently have on the ISS with CVIS, T2, ARED. So not only that, the crew will also have less time to do exercise. So together with NASA and the other international partners, we're looking at the requirements, medical requirements, physical requirements, and also at, you know, time allocated for medical tests during or in flight, but also time allocated for exercise. And I can already tell you they're going to have at least half or less time on there for exercise. Now, this is only a 10-day mission, but we know from previous shuttle flights that were also short duration that if you don't have a lot of countermeasure devices available to you, and on top of that, you don't have a super big variety in your food. I mean, I'm sure NASA Food Lab will do their best to provide excellent food, but it's not going to be as much variety as they have on the ISS. You can definitely expect to see changes in body composition, even on shorter duration flights. So, yeah, and the longer we go, the bigger the issue that will be. So, obviously, one of the big areas of focus also for the low Earth orbit missions has always been bone and muscle health. And I would like to add cartilage to that too, because I think it's always a little bit not highlighted well enough that is an issue too. So we know that this happens, and we have a quite good idea of what countermeasures are effective, but we also are seeing problems with the spinal discs. So we have had some cervical hernias and crew on the space station in flight that we had to deal with, but also coming back. And this is of course concerning, because that can be quite debilitating, the amount of pain and that can cause, and also loss of function. And on the other side, we have the cardio fitness or cardiovascular deconditioning. When we go on exploration missions, and then I'm thinking, if we don't have the right countermeasures, these risks will again be a big issue for us, and especially if you have to go down to planetary surface and perform EVAs. EVAs are not without risks, and we'll get into that later, but you know, if you drive a rover, you will not know. The Apollo cowboys had made some interesting stunts with their rover and had some near accidents, let's put it that way. So actually trauma is not unrealistic scenario when we go back to doing these things on the surface. And again, we have gravity that becomes into play. And also, performing an EVA is quite tough for the astronauts. So they're in a pressurized suit, so they're basically fighting against the suit and the pressure of the suit. And that EVA can last up to maybe 6 hours. And during those 6 hours, you can drink and rehydrate. They usually have a water bag, maybe with some electrolytes, but you can't eat, all right? And there's limitations of what you can add to your body in energy sources. So we need to make sure that our astronauts are fit when they go and do these surface expeditions. So when I talk to, especially to my exercise colleagues, I've asked them and I pushed them and said, okay, what are now these give me 2 top priorities that you want the research community to focus on? Where do we really need some hardcore answers? And this is actually what they told me. So first of all, we have another nice opportunity. ESA will deliver the Gateway exercise device. So it's going to be a European product. And we, and I mean not just ops, and the scientific community have some great opportunity to influence what that device is going to look like. But in order to make the best device that is out there, we need to know what are the minimum physical exercises in dose that our crew members need to do to maintain their performance. And then I mean VO2 max, but also arm strength. And what's the most optimal cardiovascular ergometry form for spaceflight? Is it the bike, Cevis-like structure, or is it a treadmill, or perhaps a rowing device, something that we haven't tested yet? So we really need to get some answers, and we need them rather quickly, because the TT is just opened for this Gateway exercise device, and if we want to give the engineers the correct inputs, we need to come up with the good inputs so that they can design it the way we want it, them to. But other things that we need to look at is, for example, what other smart, low mass, low volume add-ons could we add to enhance, you know, if we have less exercise devices and less time, how can we be smart to basically maybe cheat our way a little bit into it? So muscle stimulation are some things that we're already looking at. Blood flow restriction is another one. So things like this, but I encourage you to think out of the box and think out about solutions. And what about performance-enhancing drugs? I mean, yeah, it's an interesting topic, I think, to talk about, and pharmaceuticals as well. And this is where we really need your inputs as well. Another topic, fluid shift. It's a problem, or it's an effect we see in microgravity. We know it very well that this happens. So basically the cranial fluid shifts and all the side effects that come with it, and there are quite a few, right? When we see our astronauts go to space, basically immediately we see it in their faces. They get these puffy faces, and then there's a slight adaptation going on. But yeah, when you blunt those baroreflexes, and also when you go back to a gravity environment, you know, orthostatic intolerance can be an issue again. And, you know, we are also quite concerned about the risks of DVT nowadays. So there's a lot of research ongoing, operational research, because we've had a few cases of DVT. And it's not happening in the legs, it's happening in the interjugular vein. And this is not a nice place to have a DVT because, as you know, it's also connected to the brain. And having a thrombosis in this area can also not just be a nuisance, but it can actually really affect your health and performance of your crew member. So a lot of focus of our research is going into this area. So again, here is a slide with some of our top priorities at the moment. So what are the actual risk factors for developing space-associated DVT? What happens to blood coagulation in space? So these are important questions. And what countermeasures are effective? On the picture, you see the LBNP device that is used on the Russian segment. They've been using it basically since the beginning of their space flight, but they haven't used it to prevent DVT, but it was more as an orthostatic tolerance challenge test before returning crew to the ground, because that's when they have the orthostatic problems, right? When they return to gravity. So basically in the last weeks prior to return, they start ramping up this countermeasure. But now we're again looking into this, like, is that something we should do or offer our crew on a daily basis? But there are risks involved with this device. It's not without risk. You can get, if you do it too boldly, you can actually create orthostatic hypotension, and the crew member can lose their consciousness, or it can create cardiac arrhythmias. So it's not without risk. Another thing or item that the Russians have been using for a long time is these elastic bands around the upper legs to prevent this fluid shift. And they usually wear it at the beginning of the flight and then gradually decrease the use. Now NASA is also flying this and testing it on their crew members, and a lot of them like using it because it makes sure that their face doesn't get so puffy and don't have the stuffy nose effect, but perhaps it can also be an interesting countermeasure for this DVT. My concern as a flight surgeon then is like, okay, are we not just, shifting the problem to a different body part? Well, because, a lot of it has to do with fluid shifts, but also immobility, right? Because the majority of the day, they're just floating around and not really activating their muscles. And only when they do their exercise, they're actively using all their muscle pumps and that. And what about lunar gravity? Would that be sufficient to prevent this stuff from happening? And what are the best treatment options if such a case should arise? And what are the pharmaceutical effects, in a microgravity environment? And not just for DVT, but that's really across the board. And how are pharmaceuticals impacted by radiation, for example? Another big area of research, I think, that needs to go into. So I'm going to touch upon radiation because I was also asked to touch upon this topic. I know we had a very interesting discussion about this yesterday. So I want to make it a little bit more practical, like give you some scenarios. So here you see a nice solar flare. This is really not what we want happening when we have our crew venture out into deep space, right? So when we look at the health risks, and Dr. Folkman did an awesome job, and so I'm basically repeating what she already mentioned there about the various effects of radiation. So on the one side, the deterministic effects, which are very severity dependent, this is the threshold. Like if you go over the threshold, you will likely see it, and this is basically affecting a large number of cells and usually within a short latency. And then on the other side, you have the stochastic effects. So there, the probability increases with the dose, so not severity. And there is no safe threshold, yeah? So damage of a single cell can be enough to cause effects. And the manifestation is usually delayed years. So on the deterministic side, we have for example, the acute radiation syndrome, but also cataract, radiation dermatitis, and sterility. And on the other side, we have the cancer is the big topic, but also germline mutation and degenerative diseases, neurodegenerative and cardiovascular, and perhaps also cataract. That's always been a little bit of a discussion point. So when we look at it from the operation side, I'm mostly concerned with what is going to affect not only crew health when they return home to Earth and they perhaps get cancer at an earlier stage than the general population, but what is also going to affect their performance and actually increase perhaps the risk of the whole mission. When I think about it, I think of the ARS, so the acute radiation syndrome, but also cataract. And I will get into that a little bit more. But first I want to highlight some of, so Dr. Voogtman is our radiation health officer and then our expert. So I've asked her, give me your inputs, give me your areas of focus. Where do you want to prioritize the research? And she says, basically understanding the biological effects on the various tissues. We still don't have, there's still a lot of question marks. Health risk assessment, modeling, very important. We need to be better at modeling and predicting, right? And the male and female variations, for example. Monitoring, so we're already doing a great job at that. We have some great active dosimeters and various dosimeters that are going to fly on the gateway, but perhaps we also need to think about other novel biodosimeters that are more tissue specific. And then we need to think about medical relevant non-biological effects. So I touched upon it, drug and food stability. How is that going to be affected by radiation? Equipment, medical equipment. So we plan to bring an ultrasound machine to the exploration missions. You know, how is it going to operate if we're only going to have one device because we cannot bring 3, and that thing is affected by the radiation and you cannot operate anymore? That's going to be a problem. And mitigation, talked about that yesterday. So having a very good early warning system for our crew, and on the other hand, shielding when an event happens. But I also want to think about pharmaceutical and nutritional and other biological countermeasures. We need to focus on the countermeasures. We know that radiation is harmful, and we may not find out on time to what extent, but we better be working on the shielding and the other countermeasures for radiation simultaneously, because we're probably not going to have enough time to first do it sequential. We'll have to do it simultaneously. So some of the things that I want to focus on are these novel biodosimeters and also mitigation. Acute radiation, let me lose. So you said I could go long, right? Okay, so then we have plenty of time. Acute radiation syndrome. So what is that, right? So what do you need what kind of factors do you need for that to happen? So you need a large dose. I think the consensus is about 0.7 gray, but there's also discussion about that. It must be external, it must be penetrating, high energy, the whole body needs to be irradiated by it, and it must be delivered in a short time. When we think of spaceflight and we have a solar particle event, this can happen. And let me go a little bit further. Oh, this is a bit hard for you to read, I think. So one of the things that happens first with the lower amount of grays is the hematopoietic syndrome, basically affecting the bone marrow. And what are the symptoms? So one of the symptoms that you have in the beginning is anorexia, nausea, and vomiting. And that can occur within an hour or so after exposure, depending on the dose rate and the dose, right? And then highlight some of the red things here because I think they're most interesting to us. Because it's affecting the bone marrow, it's affecting our immune system, and it's affecting our our blood, our ability to transport oxygen and to coagulate. So all of these things can be affected, and death may occur at some individuals, not all, at 1.2 gray. So it can also be a secondary effect of, for example, infection due to the radiation exposure. But when you look at the very first symptoms, like the nausea and vomiting in a spacesuit, if you are on a lunar EVA, is a bad day. You cannot clean your helmet. You will not see anything, and it will vastly affect your ability to do anything. And you'll be, in need of help, but who's going to help you? Because your other buddy who's supposed to help you is probably going to be exposed to the same amount of radiation and will be probably just as sick as you are. So just taking you into a risky mission scenario. So lunar surface EVA plus massive solar particle event. It's not unthinkable. I mean, we're going to send crew within the next years. It's going to be at solar maximum. This can actually happen. Yeah. And also, we heard yesterday, we want to explore. We want to, have a bigger action radius. We want to explore more than the previous Apollo astronauts did. So Apollo 17 astronauts were the ones that were able to venture out the furthest. They went as far as 8 kilometers away from their space vehicle. But yeah, so if we're going to venture out further, it means that it takes longer to get back to your safe haven, if your space vehicle is the safe haven, right? So you really have to depend on a good early warning system. What if we're going to venture out much further? It's going to take hours before you get back to your spacecraft. So you need a storm shelter. Okay, great. But what if the solar particle event lasts for hours, maybe days? I don't know. Their life support system or the suits that are currently designed are not made for you to stay in there for days. This is hours. So a storm shelter or digging a hole, I don't know if that's going to be, again, the best option. So in 1972, there was this very large high energy solar particle event, and it got measured up to, it was 1.4 gray per hour. So when we look back at the previous slides, this actually can cause acute radiation syndrome, right, in that dose range. So I really think we need better shielding materials in the suit so that at least the crew can self-rescue themselves. So I think there is a vast, interesting area where and I think, with AstroVest, and there is already quite some investment into looking at various materials and protective equipment. I think we need to come up with some good, protective measures there. For example, I don't know if this has already been looked into. I know NASA has been looking at this. So hydrogenated boron nitride nanotubes. It's a material basically with a lot of hydrogen in it, but it can be woven as textile, and you can make, basically clothing material out of it. Will it be enough for a solar particle event of that magnitude? I don't know. Let's find out. So if we look at this slide, I hope you can read it because it's a bit small, but this is a table coming from a NASA document. So where we look at missions, so on the left side here you see Artemis 2, Artemis 3, Gateway, Mars, different Mars missions, which are the shorter and the longer duration Mars missions. And I've highlighted with the red circle, the top you have solar maximum, and the bottom you have solar minimum. And we learned yesterday, solar minimum is actually bad for Mars missions because the sun and its magnetic field protects us against these GCRs. So if we are, and this is where it becomes interesting as well, because these solar minimum and maximum timeframes are quite long. So it really depends on when you're timing your mission, and when you're ready to fly, it might actually be during solar minimum. And I highlight it again, on the top you see dose in grays, dose equivalent and effective dose. And I highlighted the Mars missions here, which are well above the current agreed upon thresholds, basically saying we cannot send any humans to Mars, and certainly not during solar minimum. And that's looking at, I can't point it, but the different shielding, so 0, 20, or 40, and this is the different grades of shielding. So even with the best shielding out there, it's not going to be enough to take our crew safely. Not if we're keeping us within these thresholds. So this is a slide I borrowed from my colleague Anna, so basically showing the currently agreed upon, basically dose limits for the various organs, so blood-forming organs, but also eye and skin. You will actually, go over your career limit during the mission if you would do this. One other thing I'd like to highlight here is cataract. So we know this from terrestrial, right? So we know nuclear workers, people that work with radiation all the time, like intervention cardiologists, colleagues of us, they develop cataract at an earlier age, but also pilots. So we know this is, the human lens is extremely sensitive, and it is actually the most radiosensitive tissue that we have. And it's both sensitive to ionizing radiation and non-ionizing radiation. And it's the opacification of the lens, and that can lead to decrease and even loss of vision. The location of a radiation-induced cataract is somewhat different than with aging. So we see it also in aging population, but there are some different aspects on the location of where it's happening. The exact mechanisms of radiation cataract genesis are still not fully understood, and there's also some lack in standardization and classification. And the only way we can treat cataracts today is with surgery. I can tell you, we're not going to have that capability. I think it's very unlikely we'll have an eye surgeon in our Mars mission. So, I'm not saying it's impossible, but I think it's very unlikely. Here's a picture from this study that was done in patients in the Ukraine after the Chernobyl accident. So we have a lot of Earth-based data out there from nuclear accidents and also bomb survivors out there. And we see that this is also happening in them, but it's usually happening years after the incident. So how much radiation dose to the eye is necessary for the production of radiation injuries? So the ICRP has accepted the threshold of 0.5 gray. I know that there's also still some discussion about that, but let's just take that. And how soon then after radiation exposure can one expect to see radiation-induced lens injuries? Well, the latency is inversely dependent on dose, and it can be as fast as up to 2 years, depending also on the individual and the preconditions and the dose exposure and the rate. So what if your Mars mission is 2 to 3 years? Do we really want to have a blind astronaut performing a landing or critical visual tasks on Mars? So I think it's an underlighted problem, and I think we need more research. Another interesting angle to look at it is the lens not a nice biodosimeter? Can it predict actually perhaps some neurodegenerative diseases? And there are some, this is also from the Ukrainian study I mentioned, they're actually seeing that there is a link there. So if you see degenerative changes in the lens, that person is also more likely to have or develop neurological problems due to the radiation. And what countermeasures do we have for that? How are we going to protect the eye? And we discussed it yesterday over a drink in the hallway, and I think, I'm not sure if you were there, but we were talking about boron glasses. Could that be an interesting thing we could develop for crew members so that they could use it to give an external protection layer? So how much time do I have? Still some time? Yeah? Oh, okay. good, so I will go a bit faster. Neurovestibular and sensory motor issues. I know a lot of research has been going on in this field, and we know that going to space affects the way we have, control and also have an experience space motion sickness. So usually in the very first days when astronauts arrive in space, they get a light schedule. And that's not for nothing. That's because it's really debilitating when you have space motion sickness. Not all crew get it, but about 2/3 of the crew in a more or less degree. And some have it very badly. And that influences your ability to perform tasks. And we also know this actually from the recent commercial Dragon flights. These are very ultra short missions. People pay a lot of money to go on those, and we are already hearing the feedback that they were not able to perform all the things that they wanted to do because they were probably affected by neurovestibular and sensory motor issues on those first days. So it's something to keep in mind. So it's not only vestibular, but it's also thinking about the visual, the eye-hand coordination. All of that's affected by a change in the gravity field. Now, when we go back to the moon, again, we're changing the gravity field. And this is some footage from the Apollo astronauts. And they had some difficulties. And it was perhaps not only neurovestibular and having no good visual references, because the moon is, we have no good visual references. It's a grayscale. You don't know if the boulder is big or small because you don't know. It's not like when we walk around on Earth and we have in our brain already implanted, oh, okay, this is approximately this big, and it really helps you to keep your balance and keep walking straight. 1/6 gravity is probably not enough to give you enough vector to have a good understanding of self-upright. On top of that, you're going to be wearing a bulky suit. So I know that NASA has been working extensively with the commercial providers to improve the suit so that they have a better range of motion, because getting up, because of lower gravity, it's a bit easier, but if you have a suit that doesn't work with you, it can be actually quite hard. So that was some of the feedback we also got from the astronauts from the Apollo missions. And yeah, it's also not great for your suit to be exposed to all that lunar regolith, right? So we don't want our astronauts to fall and tumble. We want them to operate well. Another thing you need to think about is lunar landing. So it might be an automated landing, but very likely there will be manual override capabilities, or at least that's what the crew will definitely want. So with this limited visibility and visual illusions that can be caused by lunar dust blowing up, what we call vection, is give you a very powerful sense of self-motion, and not good visual cues. It can really mislead the crew in thinking that they're going too fast or in a certain direction while they're actually not. And we need to train our crew for this. So that they can perform a good manual landing if they need to, but also to let them refrain from taking over an automated landing when they shouldn't. So we really need to expose them to this kind of training before they actually do their first lunar landing to increase the success rate. We also know from shuttle missions, even on short duration missions, the shuttle pilots, very experienced, did not do a perfect landing upon return. They often came in too fast and too far on their landing. So we know this is a thing that affects, that immediately takes effect. You don't have to be in space for months for this to be a thing. Rover driving as well. So we know from Apollo landings that there were a couple of very hard landings, a couple of near misses, some sloped landings. and some of them landed in the wrong spot, very close to a crater. And for the lunar rover drivers, they really misperceived angles. At some point, they thought when they were driving on sloped terrain, they had the feeling of turning over while they were traveling across slope. So a lot of important lessons learned that we should not forget from the Apollo missions. So one of the things that we're actually currently working on is creating this disorientation training and lunar landing training for the crew members. And this picture shows the Desdemona simulator, which is located in the Netherlands, and it can do some pretty funky things. And it's a unique asset that we have in Europe. And it's a ground-based facility for ESA, so we can all make use of it and do experiments with it to develop a good, basically, disorientation awareness program for Artemis crew. Other things that I would like to see as a priority are dose effect of partial and artificial gravity. It's always an interesting discussion with engineers who say, no, it's not going to happen, artificial gravity, and we say, okay, well, we really think gravity is really nice. It's good for humans. So we will see what happens. Also with the upcoming commercial vendors, there's going to be some interesting opportunities to perhaps look into this a bit more. Lunar dust. That's going to be, again, a thing, right, since the Apollo missions. And this was a quote from Gene Cernan, who was actually the last person on the moon. What he said in his debrief: dust is probably one of our greatest inhibitors to a nominal operation on the moon. I think we can overcome other physiological or physical or mechanical problems except dust. And dust is affecting the physiological, physical, and mechanical things, right? It's super corrosive, it's super fine, it gets into your lungs, it gets into your eyes, it's corrosive to the skin. So we know that our crew will be affected by it if we don't have good mitigation strategies to get rid of all that dust. If we go back, you see all that dust on his suit and on his face. It was all over the place in the capsule. And they didn't have a good way of basically cleaning it off, and it really sticks to the suit. Now we have the Luna facility in Cologne that will be used for training and I hope also research, because I've been visiting it and I could already feel it, and there was not a lot of exposure to me, but I could already feel it like in my throat. And that was, without kicking the dust up. And what are the late health effects of this dust? And the indirect effects, so materials. If we want to do EVAs and we're going to be operating in that environment, the suits better be very sturdy and be able to deal with that dust exposure. And other equipment as well. For example, the elevator. So this is the HLS that SpaceX is building as a lunar lander. It is super big. It's 45 meters tall. So the crew will need an elevator to get to the surface. And they're already testing this. I just hope they don't get stuck in the elevator. That would be a bad day if all the lunar dust gets into their elevator. But okay. So looking at some of the priorities again. So NASA set the exposure limits. They've done quite some testing on that already. So we kind of know the ballpark figure, I would say, where that stands. But do we really know the short and long-term health effects for short duration exposure, high dose exposure as well? And what are the effects in the long term? How can we best mitigate this? How can we objectively measure it and warn the crew? And how do we treat the crew then if they actually have these physical effects? So you've already seen this yesterday, if you were here yesterday. So this is a nice slide presenting the international collaboration going on for Gateway. Something else is going to be different compared to ISS. We're going to have a lower atmospheric environment. It's still a debate of how much lower, but it's going to be around 0.7 atmospheres. and we're going to increase the oxygen concentration also a bit to compensate for that hypobaric environment. So NASA is really looking into the most optimal combination. We obviously can't lower the pressure too much because then you have to bring up the oxygen levels, and that's, of course, a risk of flammability. And we've learned our lessons there, that we should not do that because that would be not a good day for the crew if there's a spark. Other things that I think there's a chance for Europe here, because of the vast legacy that we have with diving and decompression sickness. These are some things we also need to look into, because there are no validated procedures to adequately diagnose and treat decompression sickness in spaceflight. We're going to have, when we do the lunar EVAs, the frequency of the EVA will be much higher than when we do now on ISS. So on ISS, you do an EVA, and there's maybe, in a very specific scenario, they might have 2 or 3 a week, but that's very rare. It's usually 1 per mission for a crew member. But for the lunar EVAs, they're gonna have to go out the door every day, maybe every day for 5 days in a row. And we're going to have less time to do pre-breathes. So now we mitigate for this DCS risk by doing pre-breathe protocols. They're quite effective. But yeah, so we're going to have to change those protocols in the most optimal manner. And yeah, there are increased risks. So there's going to be some interesting research going on actually in Europe on this field. And I think yeah, some of the priorities are new pre-breathe protocols, looking into in-suit treatment protocols. But one thing I think is quite exciting is potentially vascular or tissue wearable ultrasound technology that can look for bubbles. So in the previous slide, you saw the heart and the bubbles that you can see, and you see on the right hand side, you see NASA with, I think it was SpaceX, performing ultrasound in the hypobaric chamber. And they actually did it on the Polaris mission as well to check for bubbles. And bubbles are a great indicator of DCS, and the amount of bubbles tell you more about how severe it might actually be. So perhaps this could be an interesting technology to look at, to diagnose it, but also to monitor it. I'm just putting a thought out there, and see if you pick up on it. Let's see. So with isolation, so this is a picture from Mars looking back at Earth. That's quite impressive. Huh? I really like this picture. So it's just a very tiny little star-like thing in the far distance. That is your home planet. That's everything you know. That's everything that's ever been. And yeah, what about if you're there, right? So I think this is another major thing. So behavioral health risks. How are we going to make sure that when we send the first crew to Mars, it's probably going to be a small crew, probably 4 people, that they are a very good, cohesive team. So we need to look at team cohesion and interpersonal relationships, communication within the team to the ground. The ground communication will be vastly impacted. I'll get into that due to the comm delays. But you know, there's a lot of things that still need a lot of digging into here to make sure that we have the best crew, but also the best mitigation strategies when such a problem should help. So we need to develop good screening tools for this, but also support tools to prevent and mitigate when such a thing should happen, when there's increased stress and the crew is having issues with that. And also, you know, isolation and loneliness. How does it going to affect the crew performance? One other aspect I think we need to look into is the crew that we're going to send on these Mars missions. They will need to be very resilient, but also creative, because we're going to encounter problems that we did not predict. That happened with the lunar missions, and we know that there's going to be some unpredictable events happening, and we need to have a resilient, strong crew that can handle that, but also be creative, out-of-the-box thinkers, be able to improvise when such an incident happens, and they're going to have to do it on their own because there's going to be very little support from the ground because of this, right? So here on this slide, you see the distance and the communication lag that happens when you move further away from the Earth. And from Mars, it can be up to 44 minutes. So that's, you know, if you have an emergency, that's, no, Houston, we have a problem. It's like, Mars, we have a problem, and we need to fix it here. So communication delays means increased need for crew autonomy. And there's also going to be decreased or basically no options for a medevac. Currently, we can bring back crew from the ISS if we really need to, and they can be in a hospital within 48 hours. Let's put it that way. So that's pretty good. For the Moon and Mars, we're not going to have those capabilities. We're going to have to deal with it on site. So we need research, development, and design. We need to have a robust medical care system for Mars exploration missions. It's very versatile. It also needs to be compact. Again, we're not going to have a lot of upmass volume capabilities in these small vehicles. And you need to bring a kit for the expected things that we are thinking likely to happen, but also for the unexpected things, right? So that's quite difficult to putting together a medical kit that can encompass all those needs. Yeah, we need vital sign monitoring. We need to have treatment options. And I think AI is going to be our friend here. We could really use AI to help us with making diagnoses and direct the crew in making the right decision. So some of the things that we've been working on is AI-assisted ultrasound for helping guide the crew in the right direction to make a good ultrasound, but we're also working on AI recognition. I mean, there's also technology already out there that's already assisting doctors in hospitals now to give you a good or quite good indication of what you're seeing. So is this all science fiction? So for the Star Trek Trekkies out there, this is the hollow doctor getting a whack. And yeah, and this is my colleague from NASA that was holoported to the ISS actually 2 years ago already, I think. No, it was 3 years ago already. So giving a nice greeting to the crew member in space. Yeah, so is this science fiction? No, I mean, the future is here, it's now, it's happening, and we need to really get into action mode to get things solved. So this was my final slide. Thank you for your attention, and yeah, let's have a nice panel discussion.
Thanks a lot, May-Britt. That was very, very interesting. Before we start with the panel discussion, Professor Monica Monici is going to give a very short presentation on some of the findings that I think will be a very nice input to the discussion we will have. So, Monica, the floor is yours.
So, good morning. I will show you this presentation that deals with some studies in extreme environments, in particular on the problems related to confinement and isolation. As we saw in the discussion, in the presentation before, confinement and isolation will become an important factor in the future missions beyond LEO. So, thinking to this problem, a few years ago, together with other colleagues, also together with Alexander and Judith and other colleagues, we thought that submariners could be a nice model to study the problems of confinement and isolation in astronauts. So to go on with the slides. Ah, okay. Excuse.
The green one.
Is the green, okay. So, obviously, both space agencies and the scientific community involved in the field of biomedicine is now interested to understand how protect the health of astronauts, and also what should be the profile of the future astronauts to be resilient to the psychophysical stresses they will face in the future missions. So we proposed to ESA a project about a study, a parallel study comparing data from astronauts and submariners, and why we think this is a good model. Because as you can see in this table, except for microgravity and cosmic radiation that, so obviously only astronauts are exposed, but all the other stress factors, artificial light, confinement, isolation, limitation in personal hygiene, big alterations in sleep and circadian rhythms, the alteration of microbiological profile, and also it is not listed here, but also hypoxia, are very similar on the International Space Station, but I should say on a space platform and on a submarine. So ESA selected this project, and we have all to thank ESA and to thank ASI, which funded this project and also allowed us to participate in another project, similar project performed during the Axiom 3 mission. And so we started to collect samples from submariners and from astronauts, and also to compare short and long missions effects. So so the project structure is made of parallel studies, comparing long and short-term missions and comparing astronauts and submariners. What we want to study: neuroendocrine profile and neuroendocrine markers, metabolic profile, oxidative stress and mitochondrial function, inflammatory profile, immune function and resilience to injuries, circulating microRNAs because they could be markers of some space effects, microbiome and virome. Obviously, to do this, we take several samples, several biological samples from the subject: blood, saliva, urine, skin microbiome, oral microbiome, and so on. And obviously, we scheduled session for sample collection, pre-mission, post-mission, and in follow-up. So our objectives are to understand the different impact of short and long duration missions, and also to try to have to understand what are the effects really due to microgravity and radiation, and what are the effects probably due to other factors, other stress factors during space missions that could have an important role and concur to the effects, the alterations we notice in the astronauts. And possibly elaborating this data, we hope also to be able to produce some risks, some models of long-term risk due to these effects. So, first of all, it was not easy to organize the logistics of these studies because, so more or less, we had for example, to collect samples during the mission in a submarine is quite difficult. We had difficulties similar to that you can find on the ISS, with the difference that the ISS has some facilities to do these studies. For example, it is possible on the ISS to store the frozen samples. Obviously, this was not present on the submarines, so it was quite hard work to organize this. As you can see in these pictures, we explain to the crew of the submarine, to the volunteers who decided to be involved in these studies, what we are doing, what are the samples we take, and so on. And in one of the pictures, you can see a sample collection on board the submarine. And also a colleague, one of our colleagues who is taking samples from the surface of the submarine to see what happens after the mission as regards the microbiological profile of the environment. And we have some preliminary data that I think could be a good point for the next discussion. Here we can see an increase in C-reactive protein in saliva samples of submariners after an operational mission of more than 50 days. So you can see there is a significant increase. While in a mission of about 3 weeks, so a shorter mission, we can see that we have no significant increase in PRC content in blood samples of submariners and astronauts of the Axiom-3 mission. So the length of the mission has an important impact on the increase of the low-grade inflammation in the subject. But during the study on the Axiom-3 mission, we analyzed the levels of several cytokines, and we can see that both in submariners and in astronauts, we found immediately after the mission an increase in the level of macrophage inflammatory protein 1 beta and monocyte chemoattractant protein 1. So these are important pro-inflammatory factors. The increase was resulted not statistically significant, also because the subject under study were very few, but as you can see, there is a clear trend, and we have also to consider that this is a short mission. Probably, if the mission, if the length of the mission was 5 weeks instead of 3, this factor could continue to increase. During the study, we also administered to the submariners questionnaires. These are the results we obtained analyzing the answers to the questions contained in the mood state questionnaire. We can see that they are a resilient population. Because vigor, the mood vigor is very high in comparison with the other mood states. But as you can see, there is a quite big difference between the results we had with a long mission, with the mission longer than 50 days on the left, so on my left, probably you're right, yes, on the left, and the short mission. As you can see in the long mission, the difference between the vigor mood and the other moods is decreased, and there are, so it is more nuanced. The response is more nuanced. We compared the iceberg profile of the submariners with the iceberg profile of sportsmen, because sportsmen, the top level sportsmen work a lot with psychologists on this mood state to be able to face the stress of a match, of the stress of a race. And we see that the submariners have a more resilient profile in comparison with sportsmen. This could be interesting as regards the profile a future astronaut should have. Another study we made was about the oxidative stress in these subjects. Here, for example, we studied the level of protein carbonylation, which is a marker of oxidative stress, and we saw that during and post-mission it is significantly increased, while, so this was a mission of about 50 days, while in the short mission during the Axiom 3 study, we had no statistical significance in the differences of oxidative stress before and post-mission. So, in summary, on average, during the mission and immediately afterwards, the inflammation levels are higher than pre-mission. In long missions, we have a much greater impact than in short mission on the level of systemic inflammation and oxidative stress. Protein carbonylation increases after long-term missions. And submariners are able to regulate emotions when performing under pressure. They, in our opinion, they could represent a good model to study the effects of isolation and confinement in extreme environment. And in particular, considering that, as we heard in the presentation before, considering that in the future missions, the possibility of the astronaut to connect with the family, with the friends, with the flight sergeants on Earth will be more difficult. You have to consider that the submarine missions are secret missions. So when the crews are in an operational mission, they cannot have any contact with the external world. So it is a very hard isolation and confinement condition. Another point I want to underline is that we saw that in submariners, as is reported in many studies of on astronauts, after long missions, we have an important increase in low-grade inflammation. But submariners are not exposed to microgravity and radiation. So this suggests that probably isolation and confinement and other factors, for example, the alteration of the microbiologic profile of the environment and of the microorganisms on the body of the crew is important for this kind of effect. So I want to thank all the colleagues who are involved in this study and you for your attention. Thank you.
Thank you a lot, Monica. So I invite now Maybrit, Alexander, Shuker, and Monica for the panel. Please stay on, Monica, we go. So before we open up the floor for questions, because I'm sure there's quite some questions from the audience, I actually have a question for all three of you, and I think it touches very much upon what Monica also just presented, and it's related to ground analogs. You know, you presented some data on the submariners, which seems to be a very high fidelity environment for looking into space and the stressors and how it impacts the crew, or let's say human beings. So I just wanted to ask you, all three of you, maybe you can all give a brief statement on that. What is the role of the analogs? How should we optimize the use of them? And maybe also, we have, of course, high fidelity analogs, but they usually are not so controlled. And we have very controlled analogs, which are not always so high fidelity. To give an example of the isolation studies, for example. So maybe you can also comment a little bit on that.
So this is, I don't know. It works. Okay. So this is an important question. So obviously, it is difficult to. So I think both the analogs are important. The analogs on which we have much more control and are more programmed for these studies. Obviously, because we are more sure about the results. But also these new analogs are important. So I would like to mention that ESA decided to extend these studies, and just this year, a few months ago, ESA made an agreement also with the Portuguese Navy. We worked with the Italian Navy, so these studies are less controlled, obviously, because they are doing operational missions. So they have their own objectives about this mission. But I could say that they are really stressed because they are doing an operational mission, such as the astronauts. I don't know if in a controlled environment, yes, okay, also in a controlled environment you have confinement and isolation. But probably this is not joined with a real stress due also to the activity, to the stressing activity astronauts and submariners have to perform during their actions. So in a submarine, such as in a space platform, also in a submarine, you can have some technical problems, some accidents, some unexpected events. This is difficult to reproduce in a controlled environment. So I think both the studies should be done if this is possible.
Alexander, you also have experience with working with ground-based analogs and also high fidelity, like for example Concordia, where you also have a real extreme environment. What is your take on that?
Yeah, every environment has its own peculiarities and environmental stressors that are affecting the human. I think one has to consider, let's say, a kind of suite of analogs that gives us the answer. I mean, this is always a question that we ask in these different analog environments. I mean, when you do look for bed rest conditions, for instance, you cannot, when you're always under control, there's always social interaction, you cannot very well mimic this isolation confinement element. But when you're on Concordia, this is very mission relevant, so to say, these conditions, and it's reflecting well a scenario that may really be in effect in the future. And I think the advantage of these real life analog environments, they offer, how to say, the opportunity to let the crew to organize itself, without too much control from outside. And this is certainly an asset, I would say, when we really want to think how it would be, leaving the Earth's vicinity and going to Moon and Mars. And I see as well here, and as you mentioned before in your presentation, I mean, how do we assess the crew and how the dynamics and everything? And these are environments where they take really long, a year, about 9 months of isolation, offer also the opportunity to verify as well your tools, on how, all the psychological assessments before, and face it to biomarkers or neuroendocrine responses, and to see whether this matches and whether it complements, and which of the tests may be not very helpful in the one or the other side. So it helps us in different directions, I think, for preparing, go beyond Moon and Mars probably one day, and as well as helps us to shape the tool, also the suite of markers that we need to monitor, or that we need to verify and validate, that we may use further on when we move further. Yeah.
Maybe you gave a very comprehensive overview of the operational challenges, and of course, as a flight surgeon, I can imagine that your take is very practical. You want to get results that you can implement. So how would you, see the role of analogs and ground-based research to feed into that?
Yeah, so I think all the analogs are good because they give us pieces of the puzzle, and we need all those pieces to get a pretty good understanding of what's happening and what we need to do. I think one of the key elements is standardization, and we're already working on it so that we can actually compare the different analogs better. And I think this is an effort that's being made as we speak. Because through standardization we can have an even better and cleaner picture of what's going on and which analogs may be more suited for specific subtopics. So I think we need that to get to the answers quicker because we'll have better data sets when we can compare them. Yeah.
Maybe one related question before we open the floor for questions is it's linking a little bit to things we can do to prepare as good as possible. So you've heard also the presentation from the director yesterday. We don't know what, for example, the post-ISS landscape will look like. We do not know how many crew can we include in our research. So it's going to be a little bit of a difficult time, because we need to close all these knowledge gaps and get concrete information, but at the same time, we might not have the opportunity. So analogs will play a very important role as they do today, but maybe even more as we move to this transition. One thing I would like to ask you is that we've presented also briefly yesterday is we're looking now into microphysiological models, tissue chips, organoids. I know some of you will also have experience with that, so I wonder, what could be the role of those, let's say, alternative ways of research to maybe fill the gap that we might have coming up, but at the same time still, yield important information that we might need to really understand the stressors of space and how it impacts humans. So I don't know if anybody wants to comment on really the role of those, let's say, alternative models that we could use and how you see them fitting into the overall picture.
Yeah, if you ask me, I think also alluded to it in my presentation, I think it's very important that we put efforts and research into this area and development in this area. I would love to have this type of analysis on the gateway, make it a European contribution so that we can really do way more research, because we're not going to have that many crew going, right? So we're going to have very limited data from the humans. But we can send a lot of tissue chips and different organoids and put them in that environment. So it will accelerate our understanding of what's going on there and how tissue is affected by it. And another interesting aspect is it can also often be relevant for patients on Earth. So it has it's like a double-edged sword almost. So I think it's very, very interesting, and I think we should really put a lot of effort into developing this technology further and use it.
So, in my opinion, this is absolutely important. We can learn a lot on using these tissue analogs or tissue cultures or this kind of models. Just because we can send a lot of them and have statistical significance of our experiment. So I don't know. So to say a lot of them is too much, because we know that during the space experiment we cannot use a lot of samples. But anyway, they are more than the subject. More than the subjects we can study. When we study the crews.
Yeah, I think they are very helpful tools. I think also to test for countermeasures, to have this really personalized medicine aspect, to really target the issue with the right dose and the right subject, and to find out how, to provide better care at the end of the day, and also to see whether countermeasures in which kind of may affect the system. I think this is it's a playground maybe for the one or the other, but can be really a real benefit for health in a longer duration mission. But I think this is one side of where we should go. The other side is as well, and this is real advantage, as we mentioned before, if I may complement that on the analogs, since there are few people who are investigating in a very, very distinct manner, with different teams, everyone looking at different organ systems. I don't see this anywhere else in medicine, where so many experts looking on one subject and so deeply just to the omics level and every down there. And this is an advantage I think we should really harvest even more, because this holistic view gives us really an insight how this, and where we can start modeling as well, the behavior, not behavior, but the adaptation to an extreme environment. I think this is a value that we can still harvest. I think there's still potential. And with the new methods that are developing, I think we can integrate all this into an interesting model as well, and to see whether the effects of the one or the other environment, together with all the analogs, we can really play and see how one would adjust to an environment like Moon or Mars and on the trajectory there. So it's a really interesting experience, I think, that we are approaching more and more.
Yeah, you touch upon something I think that's quite critical, which is the holistic approach. So I think in the past, and maybe still now, we are looking at countermeasures for one system, or maybe two, but we're not looking at the overall impact across the human as a collection of different systems. So I wonder, and maybe you can briefly comment on that, but how can we improve that holistic approach? I think, Maybrit, you mentioned standardization, which I think is a very good tool, because if we have, for example, standard measures across the board, this is something where we could easily monitor. If we do on board or in flight or even on ground, when we test a countermeasure, we try to validate it. If we have a good set of standard measures, we can at least assess what is happening across the board. Do you have ideas on how we could better, optimize or focus, maximize that holistic approach? Because I think that's a really critical thing that maybe we're not doing enough yet. So how can we make sure that we capture that sufficiently?
I think you mentioned that you have to think about it first, yeah. Not that we are really interconnected in our organ systems, and everyone is. It's quite normal. You have expertise in the one or the other organ system. You focus on that, but to really, leave the silo a little bit and to move right and left and up and down and see how it interacts to other organ systems. I think here in our community we're already well on this way, but regarding countermeasures, for instance, often you look just on the countermeasure. Yeah, exercise, okay, now we become aware maybe it's not good for the fluid shift, or also the heat that we may develop in the brain can be good, but can be bad. But we can be both sides. It can be a preconditioning effect, can be even protective. No one really knows. And I think the first thing is really to tackle it and to be aware that this is needed. And the other tool, or the other way also to achieve it at the end of the day, you need a very good monitoring. Yeah? You need to know which organ system is changing at which point. So, we have done studies in the ISS, for instance. The blood collections also, it's every couple of months. This is not a monitoring, this is snapshots. But if you want to monitor changes or interventions and things like that, you need to do this in a more frequent manner. And this has to be very non-invasively, of course, otherwise no one would accept this. And I think this is the challenge, to do that in a reliable way and fail-safe way. Yeah.
Yeah, if I may add on to that. So I think conferences like this are great because this is when we interact with the different disciplines. This is when we start, already acknowledging that some of the research may actually touch somebody else's research, and if we can, collaborate more and acknowledge and involve other science groups into your research to gain that holistic approach, we could do that, right? So it's not just about standardization and monitoring, but it's also really about us all collaborating and finding each other and sharing our results, or even before that, getting other scientists involved into your research protocol from a different field, perhaps, early on. Yeah.
So the problem of the holistic approach is very important, and this is the reason why we collected a large team in these studies I presented before. So we have immunologists, microbiologists, neurologists, and so on, colleagues who study metabolic aspects and so on, because all these alterations are important and probably interconnected. And I could say also the causes and concauses of these alterations are interconnected. So it is very, very difficult to understand what are the real mechanisms underlying the final effects. But it is important for us to understand this, because this is the only way to develop effective countermeasures.
Thanks. May-Britt, you gave a very comprehensive overview of, let's say, the operational challenges and also the research priorities, which I think is very helpful for the community also to be aware of those. And I know this is a bit of a tricky question, but if you would need to choose one, what would be, as a flight surgeon, taking into account also the missions that are upcoming and the challenges that we have on those, if we need to focus on one, and hopefully it's not the case, maybe hopefully we can cover everything, but what would be your key, what would be your first top level priority?
So I think, we have a near rock and a far rock, so I like to talk in those terms. So we need to target the near rock first and really make sure that the lunar missions are, covered first. And it is a stepping stone to Mars. So everything we learn from these missions should also be useful in a way for everything that goes beyond that. Wow, you really put me on the spot here. So I think in my presentation I already alluded a little bit to that. So I think if we're going to go down to the surface, first of all, we need to make sure that they land properly. Otherwise, there's not going to be a very good mission. So I do think, having a good training for the vestibular and visual illusions that may affect the crew is one thing. And of course, I also mentioned the radiation protection on the lunar surface is another one where we need to not just monitor, but also develop countermeasures, protection for the crew in case such an event should happen. So there's a few.
Well, it's interesting because, of course, when preparing for the Artemis missions, which in the first instance will be quite short duration, we are focusing again on topics that are more short, acute, short-term changes like neurovestibular, sensory motor changes. I think that in low Earth orbit, this was something that was tackled early on in the research that was done. And then we focused more on these longer duration changes, which of course are still very critical also for preparing for Mars eventually. But it's interesting that we need to shift again back to those shorter term effects to indeed prepare the Artemis missions and what's going to come up. And here I just would like to ask, because we now of course have a lot of it's a very dynamic situation, but we have a lot of these short duration missions coming up to the ISS or wherever they will fly next. So how do you see that as an opportunity, and this is a question to all three of you, to really tackle some of the key research topics? Because of course there's a very big difference between 2-week mission, 6-month mission. So how can we optimize, or let's say make best use of those short duration missions?
I would say really to mimic a lunar mission in the sense of, for example, countermeasures. And there's already some studies going on, 0T2 studies, where some crew members will not perform any treadmill exercise, for example. But for the short duration missions, the crew are entitled to use all the countermeasures devices on the station, but they are not the high priority crew members, so to say. So if there's time left, they can make use of it. But we should really make a protocol that's similar to what they're going to have on Orion and maybe Gateway, to understand, is that enough? And can they still perform a difficult EVA with some gravity if they have this, long duration, medium duration of microgravity and very little countermeasures? Yeah, so make it as real as possible. Make use of these short missions.
I mean, for you, Alexander and Monica, you're of course part of the scientific community. So, it's a very big difference if we come with we have an AO for a 6-month mission or long duration, or when we have opportunities for short. So here I would just like to ask your opinion on how can we best engage you in, those discussions, because again, the landscape is quite dynamic. Even now, we do not know what opportunities might come, but we do know that opportunities come, and they often come very short notice. So we also need to be ready to prepare for that, but scientifically that's not always easy because we need a lot of preparation and planning. So how do you see the role, let's say, from your perspective as scientists? How can we, ESA, make sure that we cater better to you, to get you really involved also in those opportunities?
Yeah, it's a very broad question at the end of the day, because there's a scientific and there's an implementation part, of course. Yeah. For the scientific part, I mean, you mentioned before, this has been done, the short flights, the shuttle missions when the ISS was built, the taxi flights of Soyuz. We have to look back, this is 20 years ago. Yeah? So science has evolved, technology has evolved. So we should really definitely take advantage of these short missions to prepare, to continue science, of course, with new questions to be asked and to be answered. And I think this is a real value now of having this again, and not just going another month more. And the other element is that we have now really this gradual durations. Yeah? It's not, in the past it was maybe 15 days maximum, 18 maybe, or 3 or 6 months, and now we have all in between. This is a real added value to really scale the adaptation. I think this is just a fact, yeah, that we should take advantage of. Regarding the implementation of scientific projects, I mean, it's an effort from all sides, of course, to adapt to the constraints of crew time and you know, the technology readiness levels. You know, how can you use this in space? Is it safe enough to use in your hardware? But I would really try to link at least the human part that we have now ahead of us. You know, when you think about exploration class missions, to use this period to well prepare, yeah, to use technology, latest technology, to adapt it, to fly it, to use it in space, in the hands of the crew, and maybe preparatory to take advantage again of the analog environments, to test it, then to fly it, and yes, to take advantage as much as possible in the remaining time of the ISS life and beyond. And I think this is what we personally would love to see. And yes, of course, I mean, one could always be faster, yeah, that's clear, but there are limitations, of course, to get ready, yeah. And I think this probably covers what I would like to say, yeah. Thank you.
So I think also now we have more sophisticated analytical techniques that can help. So for example, we have seen before that if you measure the classical clinical chemical clinical parameters such as C-reactive protein, you do not see a difference in short missions, but if you study in depth the cytokine profile, you see a difference between pre and post mission. So I think we also have now also more sophisticated techniques that can help us in obtaining interesting results, also studying shorter missions.
Thank you. I would like to open the floor for questions. I'm sure you have many questions, so yes, please go ahead.
Hi, thank you. Pete Hodkinson, Head of Aerospace Medicine at King's College London. A statement to start, I just think great panel, great discussion, and to echo some of the points from earlier, I think it's really good bringing the science and the operational teams together. So yeah, I think it's really great Space Medicine Office is getting to feed in your research priorities and needs as well. In terms of topic, to focus on the decompression sickness bit of Mobrit's talk, and I think you're right, there's a lot we can learn from diving and hyperbaric DCS world, but there's also a lot of differences with the hypobaric. So just to flag also, we have a lot of expertise in Europe in terms of hypobaric decompression sickness from the aviation side. And I'm supporting a US team who've applied to the NASA HERO DCS call around Artemis DCS risk. So the questions really are, Mobrit, can you talk more about your DCS study plans? Is that going to be internal at ESA, CNES, DLR? Are there ways we can get involved and support? Or third, are there going to be funding calls that we can apply to?
So very good questions, thank you. So first of all, yes, I echo your words. So also the hypobaric medicine has legacy in Europe, and obviously that's super relevant and appropriate as well. About the research, so I think maybe Angelique, you can also allude a little bit to this. So we, from the MedOps side, liaise with the human research team to communicate our priorities. Now it's up to the science team to make announcements, open announcements. This is how I understand, this is how we're going to do it. And then you can all come to us and say, okay, I have a great idea that feeds into this problem, and I think I may have a good research that could answer that question or help develop some technology or countermeasure in that direction. The funding part is where it gets fun, and I'll give it back to Angelique.
I think it's a very valid question. So yesterday we talked a little bit about the two streams of science that we're now, incorporating in the Human and Robotic Exploration Directorate. We have on the one side the bottom-up, which is more the fundamental research, which is of course very important, and we have a lot of very good high-quality platforms where we can really allow for excellent science to be done on those platforms. At the same time, we also have exploration objectives, and we want to be able to meet them and to deliver on them. And that's where the exploration-focused science comes in, and I think what May-Britt presented is a very good overview of what could qualify under exploration-focused research, things we need to solve or need to address in order to allow human and robotic missions to the moon, but eventually also to Mars. For those elements, and again, this is currently under discussion with our member states as well, but for those key topics where we really need to find answers in order to enable those missions and those exploration objectives, we are looking into how can we best engage with the community. This can be through directed announcements of opportunity, sometimes maybe working directly with one team because they have a very unique experience in Europe in that sense. But we're also looking into how can we fund, because historically we of course fund the opportunities. We fund access to the ISS, fly the experiment, or access to some of the ground-based analogs. But if we have a very specific question that we would like to get answered, we do not have the resources internally to do so. So we need to really rely on the community and the expertise that is there to help us to answer those questions. But then I think it's only fair that we at least also come with some sort of funding to allow for that. So again, that discussion is ongoing. I cannot give you a clear answer today, but I think it's very critical if we really want to meet those exploration objectives in a reasonable time frame, that we also make sure that we have sufficient resources to enable the community to deliver on that.
Great, thank you.
More questions, Marco?
So this is a question for May-Britt. This was really a fantastic talk. Thank you very much. And now, but you, as a flight surgeon, you will have the responsibility to implement the dose limits for the astronauts. But as you know, the dose limits are now different in different countries. So if we want to do an international mission to Mars, someone has to drop on the moon, someone has to drop before, and only Russians can go to Mars eventually. So what is your idea? How can we possibly reach an international consensus for those limits?
Yes, well, it's a good question for you as well, right? Because you are that community that sets those and develops those standards, So my colleague here, Dr. Vogtman, is here. Yeah, I think we need to reach a consensus because it makes no sense at all to have different cutoffs. Again, doing the research, standardizing it, and sharing the data is going to be crucial to get a better understanding of what are the actual dose limits that we need to have for deep exploration, because it's a very big black hole instead of a black box, I guess, where we still don't have a lot of answers. But reaching a standardized approach, I think, is very important. Yes. Otherwise, for example, we would cut out on the opportunity of ESA astronauts flying because we have a different cutoff than other agencies. That would not be fair to the crew members. And we can also not really defend it. So what is the scientific basis behind those cutoffs? We need the science to get good and hopefully rather precise cutoffs for these missions.
Thank you.
Yes, Andrew Blaber, Simon Fraser University in Canada. Just interesting talks and discussion, particularly with isolation in the submariners and so on. So I have a couple of related questions, really quick. You gave data about short and long duration missions, and I'm just wondering whether or not some of that could be reliable if you're comparing the results at the end of it, near the end of a short mission versus a long mission. If you made the same measurement in the long mission, would it be the same as the one you made at the end of the short mission because they're expecting a longer mission. And then we know we've had a number of cases recently, you know, with AX1 it was extended 2 weeks, and then of course we have the Starliner one extended. You know, if you took the same measurement with them expecting a short mission, what happened the next week after they were extended to, you know, now be 8 months as opposed to, and perhaps we may need to make these types of measurements because the validity of comparing the short versus the long may not be valid in that situation, because, you know, you always have that midsection and the last third where spirits go up because, oh, we're going to be leaving, and then all of a sudden you say, no, you can't come back for another 4 months. Those results could be completely different. So there's that psychological aspect of the isolation versus, you know, some of the physiological changes may be important to understand, and whether any of that has been done or has been thought to be done. How do you compare those?
So this is a very important point. Obviously, from the psychological point of view, to know that you have to stay isolated and confined for 4 months, 6 months, having no chance to connect to anyone is a big stress, surely. And also there is another point, that is when the end of the mission is postponed, and this is true for the astronauts. So it can happen to the astronauts and can happen also to the submariners often. And so these are very important points. We are learning, so working at these projects, we are learning all the things we have to standardize. I don't know if this kind of things can be standardized, because obviously if the end of the mission is postponed, often there is a contingent problem. But anyway, we have to, so in part we also began to face these problems in the study, and are working to try to standardize the collection of the samples, but mostly also the questionnaire to have more easy to have easier questionnaires in the sense that it take less time to fill them, but more frequent, so that we can and obviously the psychological problem is important, and this is so part of the profile of resilience of the subject, because
I just have a quick follow-on question that I think it was a very valid point that Andrew made, but we talked about resilience, and we think more about, you know, high stress, really unexpected events, you know, those types of things, which I think we need to select for and prepare the crew for. But what about boredom? What about monotony? Because, you know, when we think about a Mars mission, there's going to be a lot of that as well. So that's not a high stress type of thing, but at the same time, it can really, really play a very important role psychologically, how people will accept, you know, cope. So what are we doing there, you know, to try and mimic that? So I would just like to understand also a little bit your view on that.
I think we have some interesting comparable analogs on Earth, right? I myself am an emergency physician, and I can really relate to that. So sometimes you have a shift where there's absolutely nothing going on, and then all of a sudden the shit really hits the fan, and all the patients seem to come out of nowhere all at once, and you have to, you know, shift gears quickly. So I think there are actually some interesting analogs you can look at in your setting where you have to shift. But boredom, I also think, you know, it's really up to us to make sure that our crew have something useful to do. So we can look at, you know, we're looking at making sure that we have some food production, having edible plants on the station. You know, maintaining your garden is very good. Also here on Earth, nice. I can relate to that as well. So it's really helpful to gain some peace of mind, as nice distraction, but also in training. So training for a lunar or moon or Mars landing in situ, scenario training. You know, that keeps the crew on edge. And that is a lot of stuff that we can pre-program, and of course science. Let them do a lot of science. Don't let them go bored. Boredom is not, usually a little bit of boredom is good now and then, right? That's what we tell our kids. Boredom sometimes can be very good, but not too much, I think.
Maybe just a little comment what I realized from the personal interaction with the overwintering crew, and this is quite interesting, the human part of it. Boredom leads also to crazy ideas sometimes, which is also good, but you have to be able to live them. I mean, what you see in the winter overwintering crew, the midwinter celebrations, they shave half or something, do crazy things, or celebrating carnival and jumping different roles as we do here in our world, so to say. And we should, when you think about the long duration missions, you should have a box with crazy stuff in there, yeah, that you can play around. I think this is a part of human nature, and I realize it over mostly every winter over when you talk to the people. This is one really significant element to do useless and crazy things once in a while.
Yeah, and it's great for group cohesion, and I think also bringing your own traditions in, celebrating things helps, right?
I think we have time for one more question before we go into the coffee break. Martin, I think.
Yeah, thank you. Fantastic session. Martin Felix, Southampton General Hospital in England. I think the discussion about comparability of short-term versus long-term also, it's not just a matter of psychological factors and resilience, it's nutritional as well. You draw on reserves, you can make good when you come back on short missions, but you may exhaust your reserves, and this is greater than having a finite pool. What are we losing when we're losing muscle and bone and cartilage? And that gets into non-essential amino acids. What is essentiality? I think we need, and I hear from our discussion, we need a conceptual framework, and we don't have one, and we can't wait for NASA to offer us one on a silver tablet. We should work on something that encompasses the different elements, and that was a suggestion I actually had rather than lecturing. The discussion was around Earth analogs and what we can learn from that. The challenge there, I see the numbers are small, the numbers of observations. There's great stuff we can learn from that, but also from the number of people on missions, it's small. What are your thoughts at ESA in utilizing the information that's already out there from the medical treatment scenario? So there is, for example, a lot of stuff we can learn about radiation from bone marrow transplantation settings, where, of course, where the treatment is to kill your bone marrow, right? There is a lot of information on long-term consequences. Cardiovascular risk is increasing, and lots of things. Have you considered, or is there an appetite to integrate that information and bring that in, what is out there, to see where this goes, and will that help us inform thinking about countermeasures on protecting against radiation damage, for example?
Maybe I briefly comment, and then maybe if you want to add. Well, I think it's a very valid and good point. And from the discussion now, I think we have also some Earth analogs, and I don't mean bed rest, dry immersion, but I mean real, life situations where we can probably still learn a lot and translate that for space exploration. So that is something, I mean, Maybrit, you mentioned the emergency medicine, you know, the extreme spectrum between being very bored and have nothing to do to suddenly, you know, having 10 patients where you need to prioritize. Those are maybe elements that we at ESA need to look more into. And of course, it also applies to radiation and some, you know, things that we can learn from medicine or let's say terrestrial populations. I think this is something we probably have not optimized so much right now. And I think that this could be a very, let's say, it's almost like low-hanging fruit, because the data is probably there, but we have not yet really, I think, incorporated that to the full extent that we can. So I think this is a very good recommendation that I think I would like to take on board also for the team.
Or supplementary oxygen when it comes. I was very surprised to hear that the pressures are not yet defined, the concentrations of oxygen you're playing with to get to the right level for gateway and longer term missions. We really don't know. But what could possibly go wrong with oxygen, right? Comes out of a wall in almost every hospital. Well, a lot can go wrong. But how do we assess that? We would, for example, we ran a study on perioperative oxygen concentration. What's the optimum? We would not have found out that too much oxygen shuts down your mitochondria. You get mitochondrial dysfunction. It's a major feature in almost everything I've seen. Do we know what contribution too much oxygen during those extravehicular activities play in terms of our ability to respond?
Well, I think this is where the exploration-focused research also comes in, right? So we have these very concrete, you know, practical questions that we have. They might not always be the most innovative state-of-the-art science, but it's actually questions that we need to get answered in order to be able to do the missions and to keep the crew as healthy as we can and to de-risk, you know, some of the exploration. I think this is where we indeed need to make sure that the operational concerns, maybe they're not always the most sexy type of research, but we need to answer the questions. And I think this is where the, you know, the close link is quite important. Just we are a little bit over time, so I don't want to deprive you of your caffeine shot waiting outside the door. So I would like to thank everybody very much, in particular also the panelists, Maybrit, Monica, and Alexander. Thank you so much. Go ahead.
Okay. I would like only to add a small point. I strongly agree with the fact that it is not only a psychological factor, obviously. This is one of the causes, but it's not so absolutely. So obviously, if you compare short and long term missions, nutritional aspects, microbiological aspects are very different at the end of the mission. So there are a lot of factors that can contribute.
Thank you. We start again at 11:30. Enjoy your coffee and thank you very much.